Hi everyone, this is going to be your last tutorial for the semester. Today we're going over springs and it's a bit of a longer DGD, so there's 6 questions. I'm going to do the first 3 and then Thomas is going to do the last 3. Okay, so we're starting with problem 1. Here we have a figure that shows a fully opened trapdoor that covers a stairwell. The door weighs 60 pounds with a center of gravity 2 feet from the hinge, which is 24 inches. There's a torsion bar spring extending along the hinge axis, which serves as a counterbalance. So this is just this figure here. So for part A, we have to determine the length and the diameter of a solid steel torsion bar that would counterbalance 80% of the door weight when it's closed, and that would provide a 6 pound-foot torque holding the door against the stop shown. The stop is this little door stop at the top of the figure, which is just a little bumper. So essentially what they're talking about, this 6 pound-foot force is just making sure that the door actually is pressed up against the doorstop and not sort of falling closed. Yeah, so for this problem, we can use a maximum allowable torsional stress of 50 KSI. Then for part B, we have to make a graph showing the gravity torque, the spring torque, and the net torque, which are all plotted against the open door angle. This part might not make that much sense yet, but it'll make sense once we're actually going through the problem. So we have 3 assumptions to make for this problem. The first being that our torsion bar is straight and that the torque is applied about the longitudinal axis. The material is homogeneous and perfectly elastic within the stress range involved, so we don't have any plastic deformation. The cross-section is considered sufficiently remote from points of load application and from stress razors. So those were all of our assumptions. Now moving on to actually solving the problem, so we're getting into the analysis. If you adapt equation 4.4 from the textbook, we can find the diameter of a solid round rod, so that's our torsion rod. So this is equation 4.4, and we can rearrange that to get an expression for the diameter, just in terms of your torque and your shear stress. So here's a schematic for the actual problem here. So I have it drawn in 2 different cases. So first on the left we have it opened, and then on the right we have it closed. So on the left we have that the door is being pressed up against the doorstop. So that's that RD there is just the reaction force coming from the doorstop. It's not really a relevant force, it's just to kind of show you that it's actually being pressed up against there, so we're not going to be solving for it or anything. Here we know that our 60-pound force is 24 inches up from the axis, because in the problem they tell you that that's where the center of gravity is. We have TO, meaning torque open, is our 6 pound-feet, and that's essentially what's keeping the door up against the doorstop. And we know that our theta is 110 degrees. So then when it's closed, we have a torque there, TC, which is torque closed. And our 60-pound weight is still there. It's 24 inches away. And then you have the reaction force there. Once again, we're not going to be solving for it, but it's essentially just the door being pressed into the floor, I guess. So the problem tells us that when the door is closed, the bar is going to counterbalance 80% of the door weight. So this torque when the door is closed is going to be 80% of the moment caused by the door weight. So that moment is your 60 pounds, which is the weight of the door, times 24 inches, because that's how far away it's acting from the hinge. So then if you multiply that by 80%, you have that your torque closed is 1,152 pound-inches. We're also given that our maximum allowable torsional stress is 50 KSI. So we're going to set that equal to, we're going to call this shear allow, or torsional stress allow. And I'm converting this to PSI just because we're working in pound inches. So now we're going to use that equation that I had on the last slide and sub in our values. So our torque is 1152 and our shear is 50,000. So we can solve for our diameter, and that is 0.49 inches, and that's our answer for this part of the question. Now we have our diameter, we still have to find our length. So from table 5.2 in the textbook for a torsional case, meaning that's it's the second case in the table, we have this expression here. It's just that your angular deflection is your torque times your length of the rod, and then divided by your polar moment of inertia and your shear modulus G. And we also know this, K is a ratio of your change in torque to your change in angle, and you can set that equal to JG over L. So if you put that all together, we have an expression for L here, which is just polar moment of inertia times shear modulus over K, which is delta T over delta theta. So our polar moment of inertia is this expression here, just for a circle. So it's pi d to the power 4 over 32, and we know our d value is 0.49 inches. So if you sub that in, you have your polar moment of inertia here. For your change in torque, we're just looking at the difference between when the torque when the door is closed and the torque when the door is open. So we have those two values. Torque closed we just solved for is 1152, and our torque open is given to us in the problem. It's 6 pound-feet, but we need it in pound inches. So you just multiply that by 12. So your delta T is 1,080 pound-inches. As far as our delta theta, so our change in angle, we know that it goes from 0 to 110 degrees, and to get that into radians, you just multiply it by pi over 180, and yeah, so your value is 1.92 radians here. And we know that our shear modulus for this material is 11.5 times 10 to the 6th psi. So now we have all our values, and we can actually sub into that equation derived from table 5.2. So we sub in all of our values right here, and you have your final answer for part A, which is that your length is 115.7 inches, and then obviously your diameter is 0.49 inches. So now moving on to part B, we have to make a graph showing three things. So the gravity torque, your spring torque, and then your net torque, which is essentially just your gravity and spring torque put together. And we're going to plot that against an x-axis of the door open angle. So just as a reminder, this is our little schematic here. So first, to find an expression for our gravity torque, it's relatively simple. All you have here is your moment here. So you have 60 pounds, which is the weight, 24 inches is how far up along the door it is away from the axis. And here we have to take into consideration the angle. When we were solving for torque closed, we didn't have to put in cosine theta because the angle is 0, so that just cancels. But here it's actually open, so we have to take into account the angle, so cosine theta. And if you sub that in, you end up with an equation here of 1440 cosine theta. And the reason that we're not subbing in 110 degrees here is because if you sub in 110 degrees, all you're going to do is you're going to find a value for your torque at 110 degrees. But what we want is we want an equation in terms of theta so that we can actually plot it along all of the different degrees between 0 and 110. So moving on forward for the spring torque, we know that our torque closed at 0 degrees is 1152. And we know that our torque open is 72 pound-inches, and that's at 110. So here, essentially, what it gives us is intersection points along, like on a graph. So to find the equation of that line, we use y equals mx plus b. And so here your slope, so your rise over run, is just the difference between your two torque values, because torque is going to be on your y-axis. And that's divided by 110 degrees because that's the span on the x-axis between those two values. And then your b value is just going to be negative 1,152 pound-inches, because it's just based on our convention that we've drawn it, it's going to be a negative value, and you'll see that on the plot. So then if you sort of simplify that down, it's just this expression here. And your net torque, all you have to do here is you add your gravity torque and your spring torque equations together, and you end up with this expression here. So now to actually plot it, these are the three expressions we just solved for. I figured I would leave them up here just as a reference. And yeah, so this is your plot. This is what you end up with. The top curve there just shows you your gravity torque. It does make sense because of your cosine term that it intersects with 0 at 90 degrees. And yeah, so your spring torque is a linear equation at the bottom. It intersects with your y-axis at that 1152 negative value. Yeah, so essentially the reason for our negative and positive values is that we're assuming that essentially clockwise is positive and counterclockwise is negative. So your spring torque is working counterclockwise and your gravity torque is working clockwise. So that's why. And yeah, so your gravity and spring torque essentially have just been, it's a curve that kind of fits in the middle of the two. I would be very surprised if you had to do something like this on your exam, because it would take up an insane amount of time trying to actually like calculate individual points on the graph so that you can actually get a curve. But just to give you an idea, these are the two types of graphs. So you have your gravity torque is kind of a curved shape. It follows the cosine curve, and your spring torque is just a linear equation, and then your gravity and spring is a sum, so it's somewhere in between. So that was it for problem 1. And moving on to problem 2, it's essentially an extension of problem 1. So based on what we found, our bar for problem 1 is really long, and what we're going to do here is we're going to try to replace it with a torsion spring instead of a bar. So we're going to assume that it's made of the same material, so steel, and it's got the same physical properties. And yeah, so it says that the space available for a spring of outside diameter is up to 5 inches. So that's essentially, I don't know, based off of the casing or whatever, there's some external restrictions, and you can only make your spring up to 5 inches wide. So there's a few things we have to do. Part A, we have to determine an appropriate combination of values of D, D, and N. So little d being your diameter of the wire that makes up the coil, large D being the outer diameter, or it's not the outer diameter, but I will show you in a figure. It's kind of like to the midline of the wire thickness, kind of confusing, but I'll explain that. And then your N is just your number of active turns on the coil. So then we have to find the overall length of the coiled section of the spring that we're proposing. So yeah, that's one thing to mention, is that part A, you could have different answers here. There's not only one solution. Part C, how does the weight of the torsion spring compare with that of the torsion bar? So we're just going to compare the two. And yeah, so getting into it, we only have one assumption, and that is that the friction between the adjacent spring coils is negligible. So the spring isn't rubbing up against itself in a way that is actually going to affect any of our calculations. So first, just as a little reminder, once again, this is our schematic. It's the same as problem 1, and it just is also reminding you that our maximum allowable torsional stress is 50 KSI. So what do we know? We know that our closing torque is 1152 pound-inches. We know that our allowable torsional stress is 50 KSI. And this essentially we can use to find some more information. So we know from the DE theory that this expression is true. So your shear yield strength is 0.58 times your yield strength. So based on that, we can assume that this extends to the stress. So here your shear allow is essentially equivalent to 0.58 times your regular normal stress allow. So if you want to find that, you rearrange and sub in your 50 KSI, and we have a value of 86 KSI here. As I mentioned, there are many possible answers to this problem. So what we're going to do is we're going to assume that our stress concentration factor for the circular shape is Ki is 1.1. But if you look at figure 12.30, you can assume pretty much any of the values that are on there. Obviously, if you assume a value that's closer to the middle, you might get something that's less dramatic in terms of your values. And if you go to either end of the range, it'll get a little bit more dramatic. I'm not sure if dramatic is the right word, but that's the word that's coming to my mind right now. So I'm going to roll with it. Okay, so equation 12.16, this essentially just is an expression for your stress. So that comes from your moment, which is your torque in our case. And we can rearrange this equation to have a value of our small diameter d. So if we sub in our values here, we have that our torque closed is 1152. Our Ki value we've assumed to be 1.1, and our stress is 86 KSI or 86,000 PSI. So here we have a diameter of 0.531 inches. The problem does tell us that we have space available for a spring of outside diameter of up to 5 inches. And this is where this figure comes into play here. I mentioned that I would show you a figure later, and this is the figure I was talking about. So your lowercase d is the diameter of the wire that makes up your coil, essentially, and your large d is measured from the sort of the center line of the wire that makes up this coil. It's kind of hard to explain in words, but hopefully this figure will help you understand that. Essentially, it's the outer diameter minus 2 of the radii of that, the wire diameter. So essentially your outer diameter is this large d minus the lowercase d. So based on the fact that we know our outside diameter can be 5 inches, we come up with this expression here, and we can solve for our uppercase diameter, which is 4.47 inches. So what we're going to do here is we're going to just do a little check. So our C over D, our C value is D over D. That's our spring index. Hopefully you're familiar with this by now. So just subbing in our two values here, we have a spring index of 8.4. So if we look at the figure, we're using the round and not the rectangular curve. So looking at this figure at approximately 8.4, we have a value of Ki of 1.09, which is pretty close to 1.1. So it pretty much checks out. Just based off of our assumption of Ki, which is 1.1. So we can say that these values are okay. So we're looking for that the length of the torsion spring now that we have our two diameters. So just pulling some values from problem one, our change in moment, so the difference between the two torques. So we had it in terms of T before, but now I'm working in moments. It really doesn't matter. So it's essentially your TC minus your TO is 1,080 pound-inches, and then your change in angle, so from 0 to 110 degrees is 1.92 radians. So we have a value here of 563. And if you look at table 5.1 for bending with angular deflection, which is what we're working with because we're working in degrees or radians, so this is case 3. In that table, we have these expressions here. It's very similar to what we were doing in problem 1, except it's a little bit of a different case here. So your theta is just your moment times your length over EI. So your moment of inertia, I, is, we're using the one for a circle once again. So it's just your pi d to the power 4 over 64. And we know that our smaller diameter is 0.531 inches. So subbing in, we have this I value here. We know that our E value it came from Appendix C1, but it's just for steel. It's 30 times 10 to the power of 6 psi. So now we can actually solve for this length of the torsion spring. So just rearranging those two equations from table 5.1, you can sub in all your values. So you have an overall length of 207.8 inches. So just before I move on, the 207 inches might sound like it's really long, but we were working with the smaller diameter, so that's just like the length of the wire before you coil it. So it's not actually going to be that long. We'll deal with that in part B. So yeah, so working to find the number of active turns, N, you have this expression here. It's just your length over pi times your the uppercase diameter. I'm not really sure what to call it because it's not the outer diameter, but just think about that figure. So this is essentially figuring out how many turns you can make with that size of a coil and that length of wire. So we find out that we can make 14.8 active turns. So we've finished with part A. Now we can find an overall length of the coiled section. So that's kind of what you think about when you're thinking of how long is a spring. So the length of the coiled section, we're going to call LS. And this is essentially N plus 1 times D. It's from your textbook. Unfortunately, I didn't put in the equation number, but it's from one of the figures. If someone really wants to know where this equation came from, just shoot me a message and I will post it on the DGD, or I'll just respond to your email directly, whatever. Yeah, so subbing in our values, you end up with a length of coiled section LS of 8.4 inches. So that's it for part B. Now we have to compare the weight of the two. So your torsion bar from problem 1 and this torsion spring from this problem 2. So in order to calculate the weight, we have to find the volumes. So the active volume for the bar, here it's just a cylinder. So it's pi d squared times the length over 4. So subbing in those two values, this 0.49 and 115.7 comes from problem 1. So our volume is 21.82 inches cubed. And then to find the volume of our spring here, we're essentially doing the exact same thing. Once again, we're working with the smaller diameter. So essentially, we're thinking of it as a long cylinder if you kind of uncoil that spring. So subbing in our two values here, we have a volume of the spring of 46.01 inches cubed. So if we look at that, there's a ratio of about 2.1 here. So we can say that the volume of the spring is approximately 2 times greater than the bar. And since they're both made of steel with all the same properties, the spring can be said to weigh about 2 times as much as the bar. Okay, so moving on to my last problem, problem 3 before Hallie takes over. This is kind of a design question, so it's possible to end up with a whole bunch of different answers. So what do we have here? We have an automotive engine that requires a valve spring to control the motion of a valve subjected to the accelerations shown in the figure below. So if you look at this figure, there's essentially 3 points that we really care about. So first is being, or I guess it's really 2 points, but 2 of them are the same. So the reversal point is where the valve lift is at 0.201 inches. And that second point is the maximum on nose of cam. So it's essentially your maximum negative valve acceleration, and that happens when your valve lift is at 0.384. And then the third point, that's not really a separate thing, is just that reversal point again. So that's pretty much it. So a few things to note. The spring is required to hold the follower in contact with the cam during negative accelerations only, so that's why we're not paying attention to what's happening on the positive side of this plot. This might be kind of repetitive, but here you go. The critical point for the spring is the acceleration reversal point, which corresponding in this case to a valve lift of 0.201 inches. And a larger spring force is required at the maximum valve lift of 0.384 inches, but this force is easily obtained because the spring is further compressed. In fact, the problem will be to give the spring a high enough natural frequency without making it so stiff that the spring force at full valve lift causes objectionably high contact stresses when the engine is running slowly. So essentially all that's saying is that the force to be able to lift that isn't going to be our issue. We have to really work to increase our natural frequency as high as we can. So there's a few specifications that our design has to satisfy. 1, the spring length when the valve is closed cannot be over 1.5 inches. That's just because of space limitations. 2, our spring force when the valve is closed has to be at least 45 pounds. 3, the spring force when the valve lift is 0.201 inches, which is that reversal point, has to be at least 70 pounds. 4, the spring force at the maximum valve lift of 0.384 inches has to be at least 86 pounds, but not over 90 pounds. And this is to prevent excessive cam nose contact stresses. 5, our spring outside diameter can't be over 1.65 inches, once again due to space limitations. 6, we have a clash allowance of 0.094 inches. And our natural frequency, which is sort of what we're mostly concerned about, is it has to be at least high as the 13th harmonic at 1800 camshaft RPM. You don't really have to, this might sound a little crazy, the 13th harmonic, whatever, you guys haven't taken vibration analysis yet. But essentially what you have to take from this 7th specification is that your natural frequency has to be at least 390 hertz. You don't really have to care about the whole 13th harmonic thing. Yeah, so we have high quality valve spring wire that we're going to use, and full advantage taken of both shot peening and presetting. So because we're doing this, you can assume that the fatigue failure won't occur, so we don't have to worry about fatigue, as long as the calculated stress with the spring solid is limited to 800 megapascals. And when we're doing our calculations, we have to keep in mind that our ends of our spring are to be closed and ground. So that's a lot of information. Obviously, I'm not going to expect you to remember everything. So as I'm doing the calculations, I'll remind you of which specifications are important for which calculation. So that's the actual question here, is we have to once again determine a suitable combination of D, D, N, and LF, which is your free length. So yeah, this is a design problem. Obviously, you can come up with a whole bunch of different combinations, but I'll run you through two cases actually. So first, as usual, we have a few assumptions. First, both end plates are in contact with a nearly full turn of wire. The end plate loads coincide with the spring axis, so we don't have to deal with any offsets. And yeah, so I don't know why I thought there were going to be more. Yeah, so moving on to actually solving the problem. So for the maximum natural frequency, which is Fn, we have to select the highest allowable stiffness. So our stiffness here is just a ratio between your force and your actual displacement, so delta. And the two specifications here we care about are number 3 and 4. So yeah, I'll sort of specify where that matters. So in this equation here, we're doing a change in force. So that first value is can't be over 90 pounds, but it has to be at least 70 pounds. So that's the range of forces we're working with. And then your displacement is just the difference between 0.384 and 0.201. So hopefully that makes sense. So we end up with a stiffness of 109.29 pounds per inch. So when the valve is closed, this is your minimum force is just it's your minimum force at that reversal point, which is I guess 70 pounds, which would be that minimum force, and then you have to take away essentially your stiffness times that displacement. Essentially is a force. So yeah, so you take away that force at the reversal point. So here we have 70 minus 109.29 times 0.201, which is that displacement at reversal. And you end up with a force when the valve is closed of a minimum value, obviously, since we're working with 70 pounds, is 48.03 pounds. And specification 2 is that the spring force when the valve is closed has to be at least 45 pounds. And our values work out here. 48 is larger than 45, so we're all good to go here. So moving on, we are going to look at our spring rate requirement. So equation 12.8 is this spring rate equation here. Essentially, it's just your diameter is, once again, your shear modulus and your number of active turns. So if you rearrange here to find n, we can actually find it. So your G value is 11.5 times 10 to the power of 6. Once again, appendix C1. If you sub in everything, we don't have our diameter values yet, but we do have our stiffness and our G. So yeah, so we end up with this expression here. And then if you substitute in your C is equal to D over D expression, we have this equation here. It's essentially just simplified. You can double check with your calculator if you want, but that's what it resolves to be. So just to keep track of this, we're going to end up with a few weird equations. I'm going to call this equation 1. So we're going to forget about that for now. We'll look at equation 1 a little bit later. So our spring length requirement, it essentially has to be not over 1.5 inches when the valve is closed. And our clash allowance is 0.094 inches. So our spring length when the valve is open is going to be LS, which is your spring solid height, plus your maximum valve lift, which is that delta max, and your delta clash is just your clash allowance. And I'm putting in the less than 1.5 just because of specification 1. So if we sub in our values here, you can solve for LS. Oh yeah, so from figure 12.8 for ground ends, that's what the problem specified, is that they were closed in ground. And from equation 12.10, you have that your LS value is this. So essentially, I'm going to sub in n plus 2 times your small diameter as your LS value. And you can kind of rearrange. So we've solved for LS here. And this equation, once again, I'm just going to give it a number and we'll come back to it later. So that's where equation 2 comes from. Just comes from your spring length requirement. So now for your spring diameter, we're looking at specification 5. So your spring outside diameter can't be over 1.65 inches. So essentially, this is similar to what we did in the last problem. So your outside diameter is just the sum of your your capital D and your lowercase d. So we're going to make sure that they're not over 1.65 inches. And that's just going to be our equation 3. Once again, we'll come back to it. But moving on to our spring stress requirement. This is something that we were just given in the problem. It's not one of the specifications per se, but it's still important. We can assume that fatigue failure will not occur if the calculated stress with the spring solid is limited to 800 megapascals. So essentially that's just the 800 megapascals that we care about. So your force of the spring is F max being the maximum spring force at your maximum lift point, plus that essentially the force that comes from clash. So that's just your displacement of your clash allowance times your spring rate K. So if we sub in these values, we have everything here. 90 came from one of the earlier specifications. It's just maximum of 90 pounds. And yeah, so you end up with a spring force of 100.27 pounds. So now we're going to actually take this force and sort of convert it to a stress. So using a corrected stress for fatigue equation, so that just means they're including the wall factor. I'm not sure if you guys really covered the wall factor in class or not, but it's sort of what the textbook is saying that this equation is specific to. I'm not really going to get into it, but that's where that equation comes from. Yeah, so just before we start doing that, actually, the 800 megapascals, we're working in imperial units. I'm just going to convert that quickly to 116 KSI. So this is this corrected stress equation that I was talking about. So it's equation 12.5 if you want to look at it in the textbook. It's essentially just that, and this KW here is a shear stress factor. So if we sub in, we know our stress is 116 KSI, and our FS, our spring force, we just solved for the line above. And we still don't know our small diameter, and we don't know our C value, and we don't know this KW. So just using that, we can rearrange for our small diameter equation here. And I'm going to call this equation 4. So only one last equation before we can actually start solving stuff. So the spring natural frequency requirement, that 350 hertz, I believe, or 390, there we go. It has to be at least 390 hertz. Don't have to worry about what that actually means. You'll learn more about it next year. So your natural frequency equation here is equation 12.11. It's just 13,900 times your small diameter over your n times your large diameter squared. So if we sub in this spring index equation, so C is d over d, you end up with this essentially, and I'm setting it greater than or equal to 390 hertz because of our specification number 7. And I just wanted to note that in practice, we like to make sure that the natural frequency is at least 15 to 20 times the frequency of the force or the spring motion, just so we can avoid resonance, which once again, you'll learn about that more next year. But I guess in this problem, they're just making sure it's as high as 13 times. So whatever. In practice, we usually do 15 to 20. But yeah, so that's equation 5. And now we can actually start to solve these equations together to actually get our values. So I'm going to do this twice just to show you sort of two different options, because it's like an open-ended question, so you're going to get different values based on whatever you're choosing. Okay, so for a maximum nominal wire stress, meaning minimum wire mass and maximum natural frequency, we're going to try to satisfy equation 4 with the smallest kW possible. So this is equation 4, just as a reminder. So now we're going to look at this figure here for our kW. Essentially, this here is the preferred range with ends ground. And in order to get our smallest kW value possible, we're going to use our highest spring index value possible for this within this preferred range for ground ends. So at the very end here, here we have, we're going to take C is equal to 9. So if we continue this line up to that kW curve, and then we read off to the left, we end up with a kW value of 1.16. So this is what we're going to use. Yeah, so equation 4, we now have our kW value, so we can sub in 1.16, and we have our wire diameter of 0.152 inches. So that's the first part of our answer. We know that our spring index equation gives us this, so your large diameter is just C, which we've determined to be 9, times this smaller d, 0.152. So second part of the answer, done. We have 1.365 inches. Now I'm going to look at equation 3, which is just this, it's a check. So we're checking that our two diameters, so the sum, which ends up being the outer diameter, is less than 1.65. So if you sub in those values, we end up with 1.52, which is less than 1.65. So we're good here. Looking at equation 1, which is our equation for the number of active turns N here. If you sub in your D and your C, we end up with 2.74 active turns. So that's our third answer. And then if you move on and look at equation 2, this is just, once again, a check. So if we sub in our N and D, we have 0.72 inches, which is less than 1.022 inches. So once again, we're good here. And then finally, equation 5, this is for your natural frequency. We now have N, D, and C, so we can sub in those three values. And we have 413 hertz, which is decently above 390. So once again, we're good. Yeah, finally, we have our free length. That's the last thing that we were looking for, I believe. It was the two diameters, the number of active turns, and then your free length, LF. So your free length is the sum of a few different lengths, I guess. So LS is just that solid spring length from before, your displacement of your clash allowance, and then essentially the displacement that comes from your maximum force. Here you have to divide it by K just so that you convert it to something in inches. And we know that our spring solid height or spring solid length is N plus 2 times D. So once again, if we sub those in together, we have all of these values. Essentially 2.74 is your number of active turns, you have your diameter, your clash was given to you in the problem. Your maximum force, once again, given to you of 90 pounds. And then K we solved for earlier in this problem, and that's 109.29. So we have our free length of 1.638 inches, and that is your final answer for this solution, I guess. One last thing, they don't ask you to do this, but we're just going to check for it anyway. We're going to make sure that we don't have any buckling. So it's essentially just dependent on your free length and your large d here, your diameter. So if you find a ratio of LF over D, you have 1.2. And then if you check, it's just figure 12.10. So just to check buckling. And yeah, so here you can see that your ratio on the x-axis is 1.2, which is not even on this graph because it's just so stable that they don't even feel the need to show it. So since this is on the stable side, we can say that this sort of solution is good and we don't have to worry about any buckling. So now what I'm going to do is make this problem just a little longer, and we're going to do it again, but I will sort of speed through this because I feel like I don't need to explain the equations nearly as much, just because all we're doing is subbing in different values into these same equations. So here, instead of assuming C is equal to 9, we're just going to assume a different value. So we're working with C is equal to 7. So this is still within that preferred range of ground ends. It's more or less in the middle of that. So based on that, we have a KW of 1.21. And yeah, so subbing into equation 4, you have a diameter of, well, a wire diameter of 0.137 inches. That's the first part of your answer. Then once again, using this spring index equation, your sort of middle larger diameter is 0.956 inches. We're going to just make sure that this is within your constraints, which it is. It's just 1.093, which is less than 1.65. So you're good on equation 3. Equation 1, we're going to sub in our diameter and our spring index of 7 this time instead of 9. So you get a number of active turns of 5.25. So with equation 2 here, you're going to sub in your active turns and your wire diameter. And we find that it's less than 1.022 inches, so equation 2 is satisfied. Equation 5 is your natural frequency equation, and we have our N, D, and C values, so we're going to sub those in. And we find that, once again, equation 5 is satisfied. We are at 396 hertz, which is over 390, but it's not as good as what we had for with our first solution, where we used C is equal to 9, because we're trying to maximize our natural frequency here. So it's not as high, but it is, it does satisfy the equation, so it's fine. Then finally, we're going to find our free length. So not going to go through these equations again, just because they're identical to the ones that we did before. So adding these two together, we have this longer expression for free length. Subbing in all our values, you have a free length of 1.911 inches, which is essentially the end of the problem once again. But what we're going to do is we're going to check for buckling just in case, but I'm sure you can guess we'll be fine here. So once again, finding the ratio between your free length and your diameter gives you a value of 2, which is actually on this graph. So I guess it's a little bit less stable than the first time we did this, but it's still super stable. It's barely even on this graph. So we're good. No worries for buckling here. Yeah, so that's the end of problem 3.
Moving on to problem 4, we have an ASTM A229 oil-tempered carbon steel is used for a helical coil spring. The spring is wound with a large diameter of 25 millimeters and a small diameter of 5 millimeters and a pitch of 7 millimeters, where the pitch is the distance between the corresponding points of adjacent coils, and you can see those dimensions on the figure at the bottom. If the spring is compressed solid, would the spring return to its original free length when the force is removed? So as always, we have a few assumptions before we get into the problem. So number one, there are no unfavorable residual stresses. We have both end plates are in contact with nearly a full turn of the wire. So in other words, the pressure applied by the plates is uniformly distributed. So you can see in the schematic here, we have the two plates on the top and bottom, and we're just saying that the circular diameter of the spring, we have almost the full turn of that wire is actually in contact with those two plates. And then three, we have the end plate loads coincide with the spring axis, so you can see the force is being applied down the middle of the coils, which is along the axis of the helix in this case. So the question here is actually asking us is if we apply the force so that the spring is in the solid state, so when all the coils are touching, we need to know whether it's going to return to its original length. So one of those factors that helps us determine this is tau s, or the shear stress of the spring in that solid state. So that tau s value needs to be less than a factor of the ultimate tensile strength, so that there's no stresses in the material that are going to cause permanent damage in our spring. So you can see that tau s value is less than or equal to some sort of factor of the ultimate tensile strength, and that's dependent on whether the material is ferrous, non-ferrous, whether it's stainless steel, and whether presetting is present in the material. So your textbook says that to limit long-term set and compression coil springs to less than 2%, shear stresses calculated from 12.6, which we'll see in just a second. So it's just saying that normally the force F corresponding to the spring in solid state should be these shear stress values. And then we have our equation 12.6 that actually calculates the shear stress here. So in order for us to find out whether the spring is actually going to return to its original length, we first need to find the force required to actually compress that spring totally so that all those coils are touching. And then from there we can find the shear stress using that force. So we have our equation 12.7, from your textbook that we can rearrange to actually solve for the force, where we have this equation here. We'll notice that we're not given the deflection, we're also not giving n, which is the number of coils in our configuration. So we need to, in this case, what we're going to do is we're going to lump that deflection over n as a single term, because we have some variables and some knowledge of the situation that we're given that we can use to solve for that term. So if a spring is compressed solid, the total deflection of the spring would be the pitch minus the little diameter multiplied by the number of active coils in the spring. So if we just visualize that all those coils are being compressed together, so we have all the ends of the coils are basically touching, then we can see that if that pitch value goes closer to 0, we're not actually going to ever have a pitch of 0. We're going to have that diameter, because the pitch is measured to the center of those the curves in the coils. So our total deflection is actually going to be the pitch minus that small diameter value. And then because we don't know the number of coils in the configuration, we can divide our deflection by the number of coils, and then we can solve for that term. So we have our 2 millimeters here, and then what we can actually do is just you'll see that we can just plug that into the force equation from equation 12.7. The last value we need to solve for the force is the shear modulus, or the modulus of rigidity G. So don't get confused, they both the names for them mean the same thing. And for carbon steel, we have that at 79 gigapascals. So now we have all our known values to find the force required to compress the spring. So if we substitute that in, we find that the force is 790 newtons. So now we can find the corresponding stress. We can find that in two different ways, but first we need to find Ks. So the first method for Ks is using equation 12.4. So we have Ks equals 1 plus 0.5 over C. And then we can find our spring index, which is the large diameter over the small diameter, which we're just given in the question. So we can substitute that into our Ks equation, and we can find that Ks equals 1.1. The second method is to complete this graphically, so we can use figure 12.4. So in this case, you can see on the x-axis we have the spring index, which is the large diameter over the small diameter again, which we just calculated to be 5. And then we have the Ks curve at the bottom here. So that's the curve that we're going to be relating this value to. So if we find the large diameter over the small diameter, we know that it equals 5. So we can mark that on our x-axis and follow that up to our Ks curve. And then we can follow that over like we've done multiple times before, and we find that that Ks value is 1.1 as well. So now we need to calculate the corresponding stress from our equation 12.6 that we outlined before, and then compare it to our values for shear stress for the spring at the solid state that we went over in the first slide for the question. So we have our equation for the shear stress, and we have all our known values, our small diameter, our large diameter, our Ks factor that we just found, and then our force for the spring at the solid position is 790 that we found before as well. So if we substitute in our values, we find that that shear stress is 442.6 megapascals. And then we need to compare with equation 12.9, where we have no set in compression. And those are the comparisons with the ultimate tensile stress that we had before. So for this question, we have a ferrous metal without presetting. The question will usually tell you whether there's presetting or no presetting right in the question. So that's not something that you need to guess whether there's presetting or not. So we have our condition for the shear stress, and when you need to use the figure 12.7 in your textbook to figure out if this satisfies the condition. So we're going to be looking at ASTM A229 oil tempered carbon steel. So we have that here on our figure. And then we also know the wire diameter, our small d is 5 millimeters, so we can follow that up to our curve like we did before. And then what we're finding here is the minimum ultimate tensile strength in megapascals on the left-hand y-axis. So I follow it over, we are at approximately 1300 megapascals, and then we can substitute that into our 0.45 times that ultimate tensile strength equation, and we find that our shear stress needs to be less than or equal to 585 megapascals. So comparing that with the shear stress value that we found previously of 442.6 megapascals, we can see that it definitely satisfies the condition. It's less than that ferrous metal without presetting. So the spring should return to its original length. So we can conclude that there's going to be no permanent damage. Our stresses did not exceed that threshold, and then that ultimately that spring will return to its length, which is what the question was asking us for. Awesome. So moving on to problem 5. A helical compression spring with squared and ground ends is to be made of steel, and presetting is to be used. The loading can be considered static. Maximum working force is 90 pounds. A force of 40 pounds is required when the spring is 1.5 inches longer. Use recommended clash allowance of 10% of the maximum deflection and a steel having an ultimate tensile strength of 200 KSI. For a spring index of C equals 8, determine appropriate values for our large diameter, small diameter, our N and LF. So the first two assumptions here are very similar to what we had in problem 4. So number 1, both end plates are in contact with nearly a full turn of the wire. And then number 2, the end plate loads coincide with the spring axis. So again, those are the exact same assumptions we made for problem 4 with the spring situation we had there. And then the third one that is stated in the question is that the clash allowance is 10% of the maximum deflection. So just a definition of the clash allowance, it's the difference in spring length between the spring solid height and the lowest point of deflection the spring reaches in service. And I'll go into a little bit more detail what that actually means in just a couple slides here. So this schematic is from the problem statement. I just want to put it in here because it's really good at showing what knowns we have and the different components that we're trying to actually look for in the question. So we have our free spring length on the left-hand side. Then we have the spring with minimum load, which is 40 pounds in this case. And then we have our difference between our spring with minimum load and the length of the spring with the maximum load as the 1.5 inches there, where the load on the maximum load on our spring is 90 pounds. And so there you can see the clash allowance between the two spring schematics on the right hand side. So it's the difference between the length of the spring with the maximum load and the solid spring length. So you can see that difference there pretty clearly when we have the force of the solid and then our max load, we have that difference, which is our clash allowance here. And then we just have our knowns and unknowns. We know our ultimate tensile strength. We have the spring index from the question. The wire diameter is unknown. Same with the mean coil diameter, the number of active coils, and the free length of the spring are all unknown. So here we're just basically gathering all the information we have so that we can solve for the variables that the question's asking us for. So if we use equation 12.9, we have a ferrous metal with presetting. The question tells us that we have presetting in this case, and it's ferrous metal. If we look at the 200 KSI ultimate tensile strength, we can find that it's likely to be a carbon steel, which is 90% iron. So we have the ferrous metal with presetting. And then we'll use that same equation that we did before. So that same situation where we have our shear stress needs to be less than or equal to 0.65 of the ultimate tensile strength. Just in this case, we're using the presetting version of that. And then if we solve for that, we find that the shear stress needs to be less than or equal to 130 KSI. Then we can also consider the 10% clash allowance from our max deflection. So we can use equation 12.8 to find the spring constant K. So we've seen this equation before where K is the force over the deflection. That change of force is from the force of the spring with minimum load and the force of the spring with maximum load. And then we have our deflection in this case, or the change in length, is that 1.5 inches that you can see in the middle of the diagram. So we can find our spring constant as 33.33 pound-inches. And we can also solve for the clash allowance. And if we carry that through, we have our 0.27 inches for the clash allowance. And the last thing we can solve for is the force when solid, so the max force that must be resisted, that Fs value, where we have our spring with the maximum load, and then we're including that clash allowance change in length and rearranging that. So we have our 33.33 pounds, 33.33 pounds per inch times the 0.27 inches, we get 99 pounds. So we can then solve for the wire diameter using equation 12.6 from your textbook. So I'll rearrange that equation, and then we need to use that spring index value C to find Ks. So we know from the question that our C value equals 8, and then we also have our Ks curve, so we can follow that C value up to the Ks curve and then over to the left-hand y-axis to find Ks equals 1.06. This is the exact same way that we did it in problem 4. So if we substitute our C and our Ks values back into our wire diameter equation, we find that that wire diameter is 0.128 inches. And then using that spring index, we can solve for capital D, which is our spring diameter, and that's 1.02 inches. So we can then find the number of active coils, and we're going to use equation 12.8 from your textbook to do that. So the only variable that we don't have in this equation is our shear modulus, or our modulus of rigidity. And if we look at appendix C1, we'll find that it's 11.5 times 10 to the 6 psi. And then we also have our variables that we've already found in the question that we're just substituting into this equation. So if we carry that through, we can find that the number of active coils is 10.92. All right, so from the problem statement, we have a helical compression spring with squared and ground ends. So that's really important when we're trying to find the length of the spring. So if we look at figure 12.8 from your textbook, we have the squared and ground end situation. So we can see that LS equals the number of active coils times the wire diameter. So what we found in the previous slide was N, so the number of active coils. And remember from the problem statement, we were told that, we made the assumption that one full coil was going to be attached to the plates, so they're not going to be considered active coils. So we have the top and the bottom, which are not active. So the total number of coils is going to be the number of active coils plus 2. And so exactly what we're doing here, we have LS equals the number of active coils plus 2 times the wire diameter. So we can find that LS value as 1.65 inches. So now that we've solved for the solid spring length, we can find our spring free length. So that LF, that spring free length, is the solid spring length plus our maximum change in length plus the clash allowance. So the only thing we need to solve for is that delta max, which is the max force over our K value, which we previously solved to be 33.33 pound-inches. So that yields 2.7 inches for that delta max value. So if we just substitute those into our spring free length equation, we find that that spring length is 4.62 inches. So moving on to problem 6. A semi-elliptic leaf spring for use in a light trailer is to be made of steel having the ultimate tensile strength of 1200 megapascals, yield strength of 1080 megapascals, and a fully corrected endurance limit of 550 megapascals. The spring is 1.2 meters long and has 5 leaves of 5 millimeter thickness and 100 millimeter width. A KF value equals 1.4. When the trailer is fully loaded, the static load applied to the center of the spring is 3,500 newtons. So in problem A, the question asks us the load alternates as the trailer is driven over a rough road. Estimate what alternating load when superimposed onto the fully loaded spring would verge on causing eventual failure from fatigue. In part B, what will the maximum deflection of the spring be when loaded as determined in part A? And in part C, how much energy is absorbed by the spring in going from minimum load to maximum load when loaded as determined in part A? And lastly, part D, to what value could the alternating load be increased if only 10 to the 4 cycles of life are required? Again, we have a few assumptions that we need to make before we get started. Number 1, the end pivots apply a uniform load over the width of the spring ends. Number 2, failure does not occur at the spring ends. Number 3, the central force is aligned so as not to induce twisting in the spring. And number 4, the deflections do not significantly change the geometry. So figure 12.22 just shows the different types of leaf spring situations that we have. In this case, we have a semi-elliptic, so that's what we're going to be using for the rest of the problem. We also have a quarter elliptic, which is just a simple cantilever beam, and then we have a full elliptic as well. So for part A, one of the strategies that we can use is that we can see that each half of a semi-elliptic spring acts as a cantilever carrying half the total load. So we can basically just split it up into the cantilever situation, apply half the load, and complete the analysis in this way. So when a trailer is fully loaded, the static load applied to the center of the spring is 3,500 newtons. If we divide that by 2, we can find that our mean force is 1,750 newtons, and we can use that for the rest of this part of the analysis. So using figure 12.22b, we can find the mean stress of the leaf spring, where we have the stress equals the mean stress and the force equals the mean force. So here's our equation for the mean stress. We have our mean force that we just solved for, just the static load divided by 2. Our length is now going to be divided by 2 as well, because we have half the leaf spring is what we're using as the cantilever beam. We have our concentration stress factor of 1.4, and then our B and H values as well. So if we substitute those in, we can find that our mean stress is 705.6 megapascal. So we can then find the alternating stress using the modified Goodman equation. We're going to use a safety factor of 1 because the question states that we want to be on the verge of failure. So by applying the safety factor of 1, the spring is kind of barely reaching that infinite life situation, and we can be right on that verge of failure like the question is asking. So we can use the modified Goodman criterion graphically on the right, or we can solve for it on the left just using the equation. So we have our mean stress at 705.6, and then if we rearrange and solve for the alternating stress, we can find that that equals approximately 230 megapascals, which you can find graphically as well. So now we can use an equation from figure 12.22b, and we can solve for the alternating load FA. So obviously we can isolate for our alternating force, and then we have all of the known values that we previously solved for, or the question gives us. So we have our alternating stress, we have our stress concentration factor, and then we know the geometry of the cantilever beam. And remember, we were using L equals 600 millimeters because we're using half the spring as the cantilever. So if we solve for our alternating load, in this case we get 570, but again remember that we're treating it as we're analyzing half of the semi-elliptic spring and treating it as the cantilever, so our total alternating load is actually 1140 newtons. For part B, we're asked to find the maximum deflection of the spring when loaded as determined in part A. So again, we're using figure 12.22b, and we can use that equation to find the maximum deflection of the leaf spring when we have our alternating force and our mean force. So again, here everything's known except for our elastic modulus of the carbon steel, which we can look up and find as 207 gigapascals. And then from there, we're just substituting in our values into our deflection equation and then solving for the final deflection. So in this case, we find that it's 232.4 millimeters, and that's the final answer for part B. So moving on to part C, we're asked how much energy is absorbed by the spring and going from the minimum load to maximum load when loaded as determined in part A. So we know that work is defined by the force times the distance, and it's also a measure of energy expended. So we have energy is the average force times the distance, where we know the average force is equivalent to the mean force, which we found is 3,500 newtons. And then we also have the distance, so that's the deflection due to the force. And again, remember that we're analyzing this as the cantilever beam, so we have it's 2 times the alternating force, which is 1140 newtons. So substituting that into our equation for deflection, we find that it's 114.2 millimeters, and then we can substitute that into our energy equation and find that we have our energy is equal to 400 newton meters. So part D asks us to what value could the alternating load be increased if only 10 to the 4 cycles of life are required. So we're going to construct an SN diagram to determine the corresponding 10 to the 4 strength. So first we need to look at the modified Goodman line. So we can create our modified Goodman graph where we have our endurance limit of 550, and then we also have our ultimate tensile strength of 1200 megapascals. We also previously found our mean strength of 705.6 megapascals. So if we draw a line up to our infinite life criterion, we can find that alternating stress is 230 megapascals. On this graph, we can also draw our modified Goodman yield line. So we have our yield strength for the modified Goodman line of 1080 megapascals. So we can draw that on our y and x axes, and we'll use that line in just a second. So we can also construct our SN diagram. So we have on our y-axis, we have the yield strength, which is also that 1080 megapascals. That's also equivalent to 0.9 times the ultimate tensile strength. And then on the right-hand side, where it kind of tapers off, that's equivalent to our endurance limit as well, so that 550 megapascals. So then for us to find the yield strength at 10 to the 4 cycles, we're going to draw a line straight up from the 10 to the 4 position on our x-axis, and then we can find the corresponding strength for 10 to the 4 cycles. Just remember that this is a log scale, so when you're actually drawing it out, just make sure that you keep that in mind when you're taking this value from the graphs that you're creating. So if we transfer that over to our modified Goodman graph, we have our 10 to the 4 strength of 860 megapascals, and then we know that our ultimate tensile strength is still going to pass through that 1200 megapascal position. So similarly to how we did it for the infinite life situation, if we draw a line straight up from our mean stress and we hit our 10 to the 4th lifeline, and then we can draw straight over to our y-axis to find the new alternating stress if the load, if it was increased to 10 to the 4 cycles of life. And we can find that to be 350 megapascals for that new alternating load value. So we can then use the equation from figure 12.22b to solve for the alternating load FA, which we had already done previously in the question. We're just going to use the new alternating load that we just found. So again, rearranging for the alternating load and substituting in our known values. Again, we know the dimensions of our spring. We have our stress concentration factor of 1.4 and then the alternating stress that we just found. So if we substitute in our values, we find that FA is 868 newtons. And then again, remember that we're treating this as a cantilever beam. So we need to multiply that value by 2 to analyze the whole system. So we're going to multiply our FA value by 2, which equals 1736 newtons. And that is the final answer for this question.